Hey guys, welcome to my channel. So this is a new initiative that I am taking, and in this particular series I'm going to cover linear algebra from beginning to end from this particular book called Linear Algebra Done Wrong. So I'll post the link to the book in the description below. You can check out the book yourself. So this is a really good book. It is mostly targeted to mathematics honors student, but this book literally covers all the linear algebra that you will probably ever need, be it for machine learning, be it for econometrics, be it for pure mathematics or statistics or any other thing for which you might need linear algebra. Okay, so let's get started. Today we are going to discuss about vector space. Okay, briefly, when we talk about vector space, what it is, right? So there's this fun comment that I recently read in YouTube that, yeah, you know what they teach in linear algebra, vector space is a collection of vectors. And what is a vector? Vector is an element of vector space. So you know, this circular reference. So let's see, like, how can we go around it, and if that's all is, if vector space is just the collection of vectors, right? So a vector space is a collection of anything. Okay, so let's not call them vector already. Okay, so they have a particular set of axioms for vector space. If all these axioms, the objects that particular set V contains, if those objects satisfy all these axioms, then we'll call that particular set V a vector space and all the element as vectors. As simple as that. Okay, so now it might look a bit daunting if we start looking at these properties, right? But trust me, this is very easy. You know, for example, you just need to take an example of this vector. You probably know, right? Just a normal list of number. Okay, just a second. Suppose there's a vector 1 2 3, right? It's in Rn R3. Okay, so now we have a vector, and if you see that these properties are just properties that Rn follows or a list of number follows, and then we are generalizing them. So anything that follows this kind of properties, we will call those things also as vectors, and by doing that we can extend linear algebra to things more than just this kind of list of numbers, right? We can extend it to like all the real functions, all the polynomials, and many more things like matrices and different things that we'll encounter really soon. Okay, so to remember this, if you see till this point, okay, so the vectors, whatever the element, right, these vectors, they'll form a group. Okay, so what is a group? So in a group you have some axioms. Again, these are also set of axioms, right? But you can like group them into parts, and first grouping is a grouping of group. Okay, so what I'm saying is that these 4 axioms, whatever you're saying, in particular because of this commutativity thing, it would be a commutative group or a billion group. Now let's see in details what exactly it says. First of all, this is necessary for if this is there in a set, then only a set can be a group. Okay, so what is it says is that the order of the operation does not matter. So we have 2 operations. Okay, for these vectors, wherever we are considering it as a group, we are considering just this plus operation. Okay, so what this associativity law is saying, that the order of the operation does not matter. So u plus b plus w no matter if you evaluate these two first and then add w, or if you evaluate these two first and then add u, you will get the same result at the end of the day. So the order of the operation does not matter. Associativity, this is must. Then zero vector. Okay, so basically a zero element for a group. So what is this? So this is a particular element. If you add it to any element of that particular group, then you get the same element back. So zero is necessary for a group. Again, an inverse. So what exactly is an inverse, right? So inverse is basically for any vector v, if you add another vector called w, then you get this zero vector, right? This zero vector is same as this zero vector. Okay, so inverse is also necessary, and this is not necessary for a set to be group. Okay, this commutativity is not required, but in this particular case this is required for vectors to form a vector space. Okay, so it's a commutative group, and if you see, only their vector operations, right? You are adding vectors here, adding vectors here, adding vectors here, adding vectors here. Nothing to do with this scalars till now. Okay, so a commutative group under vector addition. Okay, vector addition. And let's look at scalar multiplication. Okay, so we have got like 4 rules for addition here. Okay, so 2 interesting things are there which you probably cannot see already. Okay, so one is the closure. Let's see if we get it here or not. Okay, closure I can't see here. Let's see if it's mentioned somewhere else. No, closure we could not find it here. Just a second. So basically when they are defining them, this operation, 2 operations, they're binary operations, right? Addition and multiplication by a number. So what it is saying that if you are talking about a vector space, so you can take any 2 vectors from that vector space. Okay, suppose u v belongs to the vector space, so u plus v should always belong to this vector space. Okay, similarly, suppose u belongs to the vector space. When you multiply u by a constant like c, so cu should also always belong to this vector space. So scalar multiplication and vector addition, they are closed operation. Okay, as I could not find it here, so I am just writing it down. So these 2 are also necessary. One is this and the second one is this one. Okay, so we are clear with this part, right? This is required for a group. So these 3 things plus this point, that u plus v should also be in the vector space. So the vectors form a commutative group under vector addition. Then let's look at multiplicative things about scalar multiplication. Okay, so what is this, right? 1 times v equal to v. Okay, now let's think about it. Why is it necessary? Because when you multiply any scalar with a vector, you do not know intuitively what to do, right? You're multiplying 1. So what if we multiplied by 1 and the vector became, sorry, it should be v by 2. This might also happen, right? That the magnitude became half. I mean, why can it not, right? Even if not exactly, but you know, the scaling factor, basically if you're multiplying by 1, then the vector preserves the whole scaling thing like we understand. Okay, that's pretty much all it says. And let's go to the next properties. Multiplicative is associative. So this is about, see, this is very easy. Okay, suppose you have got like 6v. Is it same as multiplying twice v by 3? Yes, it is. So basically whenever you have got scalar multiplication like 2 times 3 times v, you can always break it to 2 times 3v, right? Or you can always do it in parts like this. So that's all it says. Okay, so here we see that the scalar, there is only one vector and two scalar. Similarly, okay, let's not talk about it here because these two properties are together here. Okay, so here you can see this distributive property, right? This scalar is getting distributed over vectors, so it's just getting normally multiplied, as you can see from here. And similarly here the vector is getting distributed over the scalars, and this is it, right? So where are these scalars coming from, right? So I did not tell you this yet. Okay, so these scalars, for the time being, you can assume them to be just real numbers or complex number. Okay, to be more precise, the scalars alpha, beta, they belong to something called a field. And now what is a field? Okay, in a field you have got a set and two operations, we call them addition and multiplication. So addition form a abelian group over the set, and multiplication also form an abelian group, but only for non-zero elements. Okay, non-zero, because when you take the zero element and you take inverse of that particular zero element, then we can't take the inverse, right? It's because dividing by zero is not defined. So I do not expect that if you did not read about field already, that you will understand everything from just 2 lines of description or something like that. So obviously I would encourage you to go and look into some article in Wikipedia or any other sources that you can trust. Okay, so in this particular book we won't be needing this general field. So if we assume whenever there is field to be real or complex number, we are just fine. That's what the author is saying here. Okay, so there are certain things that directly follows. We said that 1 times v equal to v in the axioms, right? But we did not say something like 0 times v equal to 0, did we? No, right? So what does it mean? It means that this is not an axiom, means you can deduce it from other axioms, and similarly you can deduce other things. Okay, and in the exercise we will see how to deduce all this. Okay, let's just move on from there. Okay, let's see some examples. So this is something you already probably know, right? That Rn is just n numbers in a list. Okay, so here we are writing it as a column. There are two operations, right? Vector addition, because there is a vector, you're adding two vectors, vector addition, and multiplication by a scalar from a particular field. In this case it will be just real or complex number. Okay? So how does scalar multiplication take place in this case? It goes coordinate by coordinate. Okay, alpha times v1, alpha times v2, and blah blah blah. And similarly, while adding vectors, you just add them component wise. Okay, I hope it's clear till now, because it's, let's face it, it's just definitions till now, right? Things are going to get exciting now from here, because see, we already know this particular list of number case, right? But as I have already told you, that vector space, we defined it just to extend this concept, right? That we already had this list of numbers and we define some properties, and then we are going to look for other things that are going to satisfy those properties. Okay, now there's this interesting example that if we take m by n matrices, okay, suppose 2 by 3, okay, let's suppose 2 by 2 matrices, okay, 1 2 3 4, okay. So all matrices like this, if we make a set out of them, okay, then what will happen? We can add two matrices, right? And then we can multiply a matrix by a scalar. You know that, right? So these two operations we can already define. Addition of vector, here we are going to call it a vector, even though it's a matrix. We are going to call it a vector because it's an element of the vector space. Okay, but again you need to consider all the 8 axioms. Okay, that we have seen previously and see that whether those are being satisfied or not. If those are being satisfied, then only we'll call it a vector space. Okay, and it's pretty easy and manual task to go and verify each of them. Okay, and I hope you'll be able to do that. Similarly, polynomial. Okay, if you look at this polynomial, this is degree Tn. Okay, but look at this, degree at most n, not exactly n. Okay, it's not exactly n. And why is it so? We'll understand it pretty soon. It's there in the exercise. Okay, let me just tell you that. We'll get it there and then we're going to discuss it properly. Again, if we think about it, see this a0, a1 and all that, if those are real numbers, then that's a real polynomial, otherwise it's not a real polynomial, right? And now the question is, what are zero vectors in each of these examples, right? For m by n matrix, do you remember the definition of zero vector? Zero vector is a vector, if you add it to any vector, then you get the same vector back, right? So by the same definition, zero matrix would be a matrix or a zero vector if you add it to a m by n matrix. You'll get the same m by n matrix, right? So zero matrix is just this matrix minus the same matrix, so it would be component wise minus, so it would be just the zero matrix. Okay, zero matrix. Okay, similarly for this polynomial, you can see if you add a zero polynomial where all the coefficients are zero, then you get the same polynomial back. So here in this particular case, the zero vector would be the zero polynomial. Okay, so matrix operation, let's go to matrix operation. So what exactly is a matrix? So you are going to properly understand all the concepts about matrix when we go to linear transformation. Okay, till then you should just consider it to be a rectangular array of numbers. That is all. Okay, it has got m rows in this case and n columns, as you can see. Okay, and there's something called transpose. As you can see, if you take transpose, this 1 4 it went here, 2 5 it went here, and 3 6 it goes here. So basically your rows becomes column, right? First row becomes first column, second row becomes second column. That's all. Okay? And you can see that in a particular matrix, if you did not know already, this is row number. Okay, row number 1, row number 2. This is column number 1, column number 2, column number 3. Okay? So 1 2 3 4 5 6, and let the matrix be A. And if I tell you what is A 2 3, okay, now you have to go to the second row. Okay, because it's 2 3, first is the row number, second is the column number. Second row, go to the second row and go to the third column. Okay? The third column is basically this. So basically 8 2 3 is 6. That's all. I think it's pretty obvious and probably you already know that. Okay, so while transposing, I already told you, right, that row number becomes column number and column number becomes row number. As you can see, that row number is becoming column number and column number is becoming row number. That's all. Okay, so again, it's saying that when you go to linear transformation, you will understand more about transpose and all other things. Okay, now let's solve exercises and let's stop the video there. Okay, I think that's enough for one lecture. So as you can see, x is just 1 to 3, right? X equal to 1 2 3. Similarly, y is equal to y1 y2 y3 and z is equal to 4 to 1. And compute 2x. 2x is just 2 4 and 6 transpose, right? Because you just multiply everything by 2. Right? Similarly, 3y is just 3y1 3y2 3y3. And similarly, you can compute x, right? X is just x, 2hy is just multiply y by 2, and minus 3z. 3z is just 3 times this, 12 and 6 and 3. Okay, so if you add them component wise, then first entry I am doing, rest I expect you to do. Okay, First entry would be x is just 1, twice y is just twice y1 minus 3z. So minus 3 times 4 is equal to 12. So these two, just fill them up. Okay. Now let's see which of them are vector spaces and which of them are not. So what we have to see, those 8 axioms. Okay, it's almost like commandments, and you have to follow them no matter what. Okay, to actually get a vector space, that's all. You just follow them blindly, not like follow them, you just check for them whether they exist or not. Which of the following sets a vector space? Justify your answer. The set of all continuous function on the interval 0, 1. Okay, let's think about it. So let me just tell you a few things. Okay, what is a subspace here, even though we'll get the idea later probably again. Okay, subspace is a vector space subset of a vector space which is a vector space in itself. Okay. So basically it's a subset, but at the same time it's basically a subset of a vector space. At the same time it itself is a vector space. Is it clear? In itself. Okay. So you can easily go and check. Okay, like if I take all the real value function from R to R, okay, so f from R to R, then these functions form a vector space. Okay, collection of all such functions form a vector space. So how do we define addition? Suppose f plus z, okay, this is of x, so we define it to be just fx plus gx. Okay, vector addition is defined now. Similarly, we need to define multiplication by scalar, right? So what would be like our lambda f of x? It would be just lambda times fx. Okay. So we have defined scalar multiplication as well. Now that these two are defined, you can go and check for all 8 axioms and they will pretty easily follow. Okay. Now to check whether a particular vector space is a subspace or not, it's very easy. You just need to check for 2 things. Okay, I just forgot to mention a very simple thing. The zero vector in this particular case, function from real to real, that is just the zero function. Okay, so the 0 of x is equal to 0. So for any x, it just keeps out 0. Okay. So what I was talking about is that to check whether a particular subset is a subspace, it's very easy, you know, because it's already a part of a vector space. So many things come by default, like associativity, right? Suppose there are 3 elements in my subset of the vector space, right? X, y, and z, and you know they're already a part of the vector space, right? So associativity will follow by default. So this is going to happen because this live inside the vector space. These kind of properties come by default. We just need to check for 2 properties. Okay. First of one is, if I take any 2 vectors u and v belongs to the subspace or subset, then u plus v must also belong to the subset. Similarly, if u belong to the subset, then for all lambda u should belong to the subset. If anything does not directly follow from here, then you can just, you know, conclude that this kind of check won't hold, but that is not the case. Just these 2 property, and you can even condense them into one. Okay, you can say for all uv belongs to x, for all lambda and beta, lambda u plus beta v must be inside S. So these 2 conditions are equivalent to this condition. That is also I am going to prove in the next lecture or the lecture after that. Okay. So here let's go back to the question. The set of all continuous function on the interval 0, 1. Let's think about it. Let's do this test. Okay, if you add two continuous function, do you get another continuous function? Yes, the answer is yes. So first is satisfied. If you multiply a continuous function by a scalar, do you get a continuous function back? Yes. So this is a vector space. Okay, now let's think about it. The set of all non-negative function on the interval 0, 1. Suppose there is a non-negative function, so for all x it spits out a value which is greater than 0 or greater than equal to 0. Now if I multiply it by a negative lambda, because that should also be a non-negative function, right? Because this is our particular set, but that is not the case, right? If I take a non-negative function, for example fx equal to 2, for any x it gives me 2. What I have done is that I have multiplied it by minus 2, so minus 2f x. Now that is just minus 4, correct? Now it's not, this minus 2f is not a positive function anymore or non-negative function anymore. So this is not a vector space, because in a vector space you take any vector and multiply it by a scalar, then it is again a vector, okay, of that particular vector space. So in this particular space only positive non-negative functions are vectors, but if we multiply it by minus 2, then it is not non-negative anymore, and now it is not part of that particular space. So as a whole, that the whole set that we have been calling a space is actually not a space. That's all. Okay, so now this is very interesting. The set of all polynomials of degree exactly n. Okay, we just talked about it recently, right? Why exactly n does not work and it should be at most n. Because see, if you get two polynomials, one is x cubed plus twice x plus 1, okay, and the second polynomial is minus x cubed plus twice x minus 1. If you add them up, right, this is u, call it the vector u, call this vector v. If you add them up, what do you get? You get 4x. What's the degree? It's just 1, right? So if you add two vectors, you should get another of the same type, so both of them are exactly degree 3. But when I added, did I get something of exactly degree 3? No, I did not, right? So all polynomials of degree exactly n does not hold, because if you add them up, sometimes things get cancelled out and higher power may go away as well. But if it's at most n, then you know, like no higher power can come from adding up or multiplying by some scalar, so that would still hold. But in this case, this is not the case. Similarly, the set of all symmetric matrices, right, such that AT equal to A. Now what are they asking? That is it a vector space? Now let's think about it. Okay, if you take two symmetric matrices, okay, that are A and B, okay, now A plus B should also be symmetric. Now let me do the transpose. Okay, what do you get if we do a transpose of A plus B transpose? If you just look at the definition of transpose carefully, then it should be pretty obvious that this is nothing but A transpose plus B transpose. Okay, now if you see, then it's pretty evident, right? Because A transpose equal to A and B transpose equal to B, because both of them are symmetric matrix. So A plus B, when you took transpose, it remained the same. So A plus B is also symmetric. So one is done. Okay. Similarly, if you multiply any symmetric matrix, suppose A, with a scalar C, and you again take transpose, what you will get is just CA. Okay, you will get CA transpose. Again, A transpose is A because A is a symmetric matrix. So CA transpose equal to CA. So from here we know that CA is also a symmetric matrix. So basically we get it from here that sum of two symmetric matrices are symmetric matrix, and similarly if you do scalar multiplication, then also you get a symmetric matrix. So from here we can conclude that symmetric matrix are a subspace of all the matrix in case they form a vector space. But we already found in the example that m by n matrices under addition and normal scalar multiplication, they form a vector space. So this particular subset of those all matrices of a particular order, they form a subspace. So it's a vector space on its own. That is correct. True or false? Let's think about it. Okay, and this should be very interesting. So once I read the questions, or once you read the question, then you just try pausing it and try answering it yourself, okay, before looking at what I'm doing. Every vector space contains a zero vector. Is it correct? Yes, it must, right? By axiom, if you see, there should be a zero vector. It's directly there. You do not even have to do anything. So it's just there. Okay. A vector space can have more than one zero vector, but this is not true. Let me show why. Okay. Suppose it has got two zero vectors. Okay. Let me call them 0, 1 and 0, 2. Now what is 0, 1? It's just 0, 1. Okay. And you know, if you add zero vector, nothing changes. So if I add 0 another this 0 to 0, 1, then 0, 1 should not change. It should be 0, 1 only. But think about it. If I am adding a 0 to 0, 2, this is a 0, right? So if I am adding this to 0, 2, 0, 2 should not change. So it should be 0, 2 only. So now if you see, the 0, 1, 0, 2 are same. So it cannot have more than one zero vector. So this is false. Okay. M by n matrices, m rows and n columns. This is its definition. Okay. F and G are polynomials of degree n, then f plus g is also a polynomial of degree n. This I just explained that this is not necessarily true if you look at this example. So this is false. Okay. F and G are polynomials of degree at most n, then f plus g is also a polynomial of degree at most n. This is correct, right? Because if you add two polynomials of 3 degree, you cannot get a polynomial of 4 degree, you know, because the addition would be component wise. So x to the power 4 terms are not present in any one of them. So it won't just come out of thin air and like boom, x power 4, I'm here, ha ha ha. No, that's not gonna happen. Okay. Now let's look at the last few questions. And okay, prove that a zero vector of a vector space is unique. This I have already proved, right? A vector space can have more than one zero vector. This particular proof, that's all. What's the matrix? What matrix is the zero vector of the space M2 by 3? We just answered it recently, right? That it would be the zero matrix, because if you add a zero matrix to any matrix of this particular order, and the zero matrix should also be of 2 by 3 order only, basically two row and 3 columns. So 0, 0, 0, 0, 0, 0. Okay. If you add it to any matrix of 2 by 3 size, then you get the same matrix back. So that with a zero vector. Why are you calling it a vector? Because this matrix is also a part of a vector space, because all the matrix, they form a vector space, as we have seen already. Prove that additive inverse defined in axiom 4 is unique. Okay. Now this looks interesting. Okay. Okay. Suppose we have a vector v and it has got two additive inverse. One is w dash, one is w double dash. Okay. Now let's see what is w dash. W dash, I can write it as w dash plus 0, right? Because if you add zero vector to any vector, then it would remain the same, right? Now what is zero vector? Zero vector is nothing but if you add the inverse to a particular vector. Okay. So 0 I can write it as p plus w double dash, because w double dash is inverse of v, correct? So if you add them up, you get the zero vector back. Now from vector associativity, you see this is just w dash v plus w double dash. This is nothing but the zero vector. Okay, and w double dash, and from here you get w double dash. So this is equal to this. So here I am using commutativity without explicitly stating it, but if you exactly follow the axioms, then probably there might be 1 or 2 line more, but you got the whole idea of the proof. Okay, that is done. Now 0 times v equal to 0 for any vector v. Okay, how do you prove that? Remember, this is not part of those axioms, right? We just got 1 times v equal to v, that's all. Now let's try proving it. What do we know about 0? That 0 is equal to 0 plus 0, right? I can write 0v equal to 0 plus 0v, right? Now if you distribute this vector over the scalars, we get 0v plus 0v. Okay, now what we can do is that for this particular 0v, if we add inverse on both sides, okay, now why it's allowed, I did not explain it yet, why adding inverse to both sides is allowed. So basically the proof would be that if z equal to w, then prove that x plus z equal to x plus w. Okay, so this proof is also pretty easy. Okay, as you can see already probably how you're going to do that, but okay, let's keep it for another other time. Okay, now if we just add inverse to both sides, this would be just 0v plus 0v inverse, that would be just 0, and one of them would just get cancelled out, so you get 0v. Basically you got 0v equal to 0 as you needed to prove that any vector v is additive inverse minus v is given by minus 1v. So if you take any vector v and if you add additive inverse minus v, okay, so what's the definition of an additive inverse? If you add that inverse to a particular vector, you should get 0. Okay, so for v, it's saying that minus 1v, if you add it, then you should get 0. Let's see whether we get 0 or not. Minus 1v. Okay, so you can write v as 1 times v, as we got it from the axioms, right? And now what you can do, opposite of distributivity of vector over the scalars, so it is just 1 plus minus 1 times v. Okay, so now if you this follows from the field axioms, okay, as I have talked about fields already. So this is just the addition operation of field, and this is an element of field, and this is the inverse of that element, or you already know 1 minus 1 is 0, right? So this is 0 times v. We just have proved that 0 times v equal to 0, right? So see, if you add this particular thing with v, you get 0, so this better be the inverse of v, and we write the inverse as minus v, so minus v is equal to minus 1 times v. So I have given a rough outline of the proof. You need to brush it up a bit so that you know it's absolutely rigorous. Yeah, I think we have solved all the problems, and that's all that I had to discuss about vector space. In case you have any doubt, please do reach out to me in the comment section. If you like the video, press the like button, and please consider subscribing to my channel, because it really motivates me to put out good contents regularly. And that's all for today. Thank you. Bye bye.